Yes. Yeah.
Okay. So at first we will start with the definition of vitally covered. So our target here in this section is to start from vitally covers and then establish the fundamental theorem of calculus at the very last. So this is the basic target of the
Your
presentation.
voice sound is very volume is very feeble. I hope it's recording. Uh,
So can you listen to me now better?
yeah, yeah. Now it's better. So
Okay,
can you
sir.
do something about it? It was very feeble. I
Okay,
don't want
sir.
to.
Okay, sir.
I don't want to use external speakers. Then I don't know whether it will record properly. So.
Yeah, sir. Fine, sir. Yeah. Okay. So now, at first, we will start with the definition of a vitally cover. So let's consider a subset of real numbers, say A. Now, a collection of intervals I is said to be a vitally cover of A. Uh, I means here the italic I, Ci, mathcal I. So if for all epsilon greater than 0 and for all x belongs to A, there is an interval I belongs to the collection of intervals Ci such that x belongs to I and lambda of I is less than epsilon, then the cover I is the mathcal I is called the vitally cover of the set A. So now uh, after establishing the definition, we will now have a look at a lemma. So the lemma states that if a set, let A be a set of finite Lebesgue measure and mathcal I be the vitally cover of A, uh, then for any given epsilon greater than 0, there is a finite disjoint collection I1 to In of intervals in mathcal I such that lambda of A minus union k equals 1 to n In is less than epsilon. Okay, so now in this case, we can see that here the collection I contains, we need to show that there is a finite disjoint collection. So now to undergo this process, to show this, at first we need to have some assumptions. So without loss of generality, we can just assume that because it has been done in class also previously, that any interval in the collection I, mathcal I, is closed because this holds as any singleton has Lebesgue measure 0. So we are not interested with measure 0 intervals or measure 0 sets. That's why we're taking it to be closed. And there is an open set U of finite measure such that it contains the set A and every interval I in mathcal I. So now, how do we want to prove it? So our mechanism is via induction. So let's take I1 to be an interval in the collection mathcal I. And now let's suppose the next n elements, say suppose we are taking I1, I2, I3, and up to In, and are already chosen in I. Now we can have the following two cases, that either A can be contained inside the union, the finite union of these intervals, then of course A minus union of k to 1, A minus the union is phi, and lambda of phi is 0. So like it's no use. So in this case, we can easily do this. So this case is satisfied. So now the case two is the if we consider the otherwise case. So if it is not contained inside it. So then let's consider the following set Sn such that it's the supremum of lambda I such that I belongs to I and I intersection Ik is phi. So we are basically taking all possible the we are at first taking the intervals with which the intervals we have already considered, the INs, I1 to IN, those are non-empty. The intersection is empty, and then we are taking the supremum of all possible supremum of the measures of all possible intervals. Now let us recall that in our assumption B, we have assumed that there is an open set U of finite measure such that it contains A and every small I belongs to mathcal I. So that means we have, by assumption B, we have like lambda of I belongs to I. So now U contains all possible I. So lambda, as U is a finite measure. So lambda I is less than infinity. So supremum of all these things that will also be less than infinity. So Sn will be less than infinity. thus we have Sn is less than infinity. Now let us choose another set, another interval, in plus 1 belongs to math cal I, such that it is disjoint from the collection we have already considered, the n elements, I1 to in, i.e. is the intersection is 5, and lambda of in plus 1 that is greater than Sn by 2. Now again, there can be two possibilities. There exists n after which the process will be terminated. I mean, after some nth step, capital Nth step, A will be contained inside the union. So that means if A is contained, because we need to show that there exists a finite collection of intervals. So if we can find a capital N such that this A is contained inside the union, then it means by the previous argument in the case one we did already, lambda of phi will be 0, and thus we will be done. So as previously done this case. And if we can't find any such n, capital N, so the process doesn't stop. So now we have an infinite sequence, in such that n belongs to n of intervals satisfying the above properties. So now, shall I continue? Shall I continue, sir?
Yeah, please continue.
Yeah. Okay, sir. So now in this case, we have the following observation. Now, as all the ins are disjoint, because we have considered we have constructed the collection to be disjoint by our previous assumptions and constructions. So now this will be additive. That's why summation will be equals to the union, and now this will be less than infinity. This will be less than equal to lambda of capital U. The capital U is the set we have already considered above. So this will be a finite. This will be a finite measure. Now, why does this hold? Because we know that as we have constructed the capital ions, they are contained in U, as every A and every I is in U. Thus, this will be less than equal. The union will be less than U, lambda of U, and thus it will be less than infinity. It will have finite measure. So moving on. Now, let any epsilon, a given epsilon greater than 0. So there exists a capital N such that summation n equals to n plus 1 to infinity, lambda of in is less than epsilon. Now let us consider the following set. Capital L equals to a minus union of n equals to 1 to n, union of in. So now note that as each of ins, the small ins belonging to the math cal I is closed by A, by our first assumption we did in the very first line of the proof, then their finite union will also be closed. So now observe that math cal I is a vitally cover for A. It follows from definition that for any x belongs to L, there is an interval I belonging to the collection, the vitally cover, the collection of intervals I, math cal I, that contains x and does not intersect with the finite union. That is, there exists I belong to I and x belongs to I such that I intersection union n1 equal n1 to n in is equals to phi. Now we have the following observation. If I intersection ik is phi for all k less than equals to n, then lambda of I is less than equal to Sn, less than equal to 2 lambda of I plus n. And why does this hold? This holds because just we have considered lambda to be greater than Sn, sorry, lambda of in plus 1 to be greater than Sn plus 2. So thus 2 lambda of in plus is greater than Sn. Now let us observe what was Sn. Sn was a supremum of all such I belongs to I such that I intersection ik is equals to phi. So thus, of course, this is valid because lambda of I Sn is the supremum and I belongs to that collection. I is an element. So the supremum will always be greater than any element. It is by definition. So any lambda I that will be less than equal to Sn less than equal to 2 lambda of In plus 1. And our second observation is lambda of In as a sequence. Let us consider lambda of In equals to capital An, I running from 1 to infinity. This converges to 0 as n tends to infinity. And why does it converge to infinity? Because all we have here that there exists a n for any given epsilon greater than 0, such that summation n equals to 1 to infinity lambda of I by n is less than epsilon. So now the choice of epsilon is on our hands, so we can make it epsilon by n, and like that by using sandwich theorem we can show that each and every interval in will actually go to 0. Lambda of in will actually go to 0. So now there exists an integer greater than integer k which is necessarily greater than n, such that now why is it necessarily greater than n? Because if it is less than n, then this thing will arrive again. So like we are looking at another case such that I intersection ik is not equals to 5. So now without loss of generality, we can assume that the k is the smallest such integer to exhibit the above property. And now why can we choose the smallest integer? That is because of the well ordering principle. For well ordering principle, the minimum element exists, and by that we can say that we can assume that k may be the k let k be the smallest. uh, Let mk be the midpoint of the interval ik. So now let us observe that x mod of x minus mk, that is less than equal to lambda of I plus half of lambda of ik. Now why that is half of lambda of ik? Because uh, I mean this is just the Lebesgue measure including the triangle inequality thing. So and then sk minus 1, and why it is less than sk minus 1? Because lambda of I is going to that set we have considered before, and we have considered Sn before. So from there we are having sk plus 1, sk minus 1, sorry, because we have considered here ik. So it's in plus 1 is greater than half of Sn. So that's why this thing is coming. Because in the next step we will have this. This is n equal to 2 lambda of ik plus half lambda of ik, which is equals to 5 by 2 lambda of ik. So now let us call this relation as double star. Now let Jk be an interval in R such that it has midpoint Mk but has 5 times the length of Ik. So now why are we considering 5 times the length of Ik? Because here we have x minus Mk, the mod, that is less than equals to 5 by 2 lambda of Ik. So it's 5 by 2 lambda of Ik. So basically it's half 5 into lambda of Ik. So like if we increase the length 5 times, so it will basically become x minus mk less than equal to half of lambda jk. So now thus we have that L, the set L we have constructed before, a minus summation in union n equals 1 to capital N in, that will be contained inside the infinite union k running from n plus 1 to infinity jk, from this thing, from this x minus the double star which is thing. Thus we have that lambda of L. From this we have that the before relation, this is just the preceding relation. Lambda of L will be less than equal to lambda of union k running from k equals to n plus 1 to infinity jk. That will be basically, as this is not the intersection is not 0, not 5. So thus it will be less than equal to this, and which will basically become summation k equals to n plus 1 to infinity 5 lambda of ik. by construction of jk as we have constructed jk, which is less than equal to 5 epsilon, because we already have that lambda of in converges to 0. This lambda for every epsilon greater than, for any given epsilon greater than 0, there exists a capital N such that by the definition of limits, we can show that. Thus, we have that this lambda of ik will also be less than epsilon for any k greater than capital N, and this follows because k is from n plus 1 to infinity. So it is less than equal. This will be less than equal to 5 epsilon. So now, as we have chosen epsilon to be arbitrary, thus this completes our proof because L was a minus that finite union we have considered. Thus we have a finite collection n running from 1 to capital N in such that this thing holds. Sorry, yeah, such that this relation holds. Lambda of a minus union n running from 1 to capital N in is less than epsilon by the very last statement. So now, as our target of this section is the fundamental theorem of calculus, and so thus we need to. Can I stop screen sharing? I have another file. I will share.
Yeah. Good.
Yeah. Yes. So now, so thus, for fundamental theorem of calculus, we need to have the notion of differentiability, differentiation, how it makes sense, and what does it say. So now we have already studied differentiation in previous years and in junior classes, pre-college. But now we will study them via measures. So now let's take what is the definition of a differentiable function on R. So let us take two real numbers a and b and define a function from the compact interval a comma b to R. Now the function f is said to be differentiable at a point x belongs to the closed interval a comma b. We can consider it open also. If f dash x is equals to limit h tends to 0, f of x plus h minus fx by h, this limit exists. And now we say that the function is differentiable on the whole of R if this is differentiable for all x belongs to R. F dash x makes sense for all x belongs to R. Then we say the function is differentiable. Okay. So now just some terminology we will use later in the proofs. Let us denote the right derivative as Rd of fx, that is limit h is into 0, f of x plus h minus fx, and the standard definitions. So now in the later part, when we will prove the theorem, which will be the at the very last of my presentation, there we will need the d power d plus f of x, not the sub the up one fx, and the d minus the sub one fx. So these two will be required. So particularly this one, and this one, because we will show this for a single set, and then because this thing holds for all the other sets similarly, by the same argument we will show, we will be proving the thing. Thus, for the rest cases, we can do it similarly, and hence this can be covered for the whole thing. That was that is what we are going to talk about now, theorem 1. So let f be a non-decreasing real valued function on the compact interval a comma b. Sorry. Then the following three holds. F is differentiable almost everywhere. The derivative f dash is measurable, and integration a to b f dash x dx is less than equal to fb minus fa. So now a very important thing to notice here is that f is a non-decreasing real valued function. This thing will be used a lot in the later portion of the proof. So now, for the first part, we have we have to show that f is differentiable almost everywhere, and the second part, derivative f dash is measurable. So now we intend to do both of this at once. How? So if we can show that where the set where the derivatives disagree, because I forgot to write it here, or maybe I forgot to scan it. I can't remember what. So how when does the derivative exist? When d plus power plus and d sub plus, they agree and become equal, and d minus and d minus, they become equal and they equal rd of fx and respectively ld of fx. And when rd and ld of fx, they both equal, they they are equal, then we say that the function is differentiable at the point x. So if if d plus d power plus d sub plus d power minus and d power minus sub minus, they disagree at some point, or in some collection of points. So we intend to show that that collection of points has measure zero. So by that we will be able to show that all those points where f dash doesn't exist has measure zero, and all the other points has measure, finite measure, or at least a measure, not measure zero, not a non-zero measure. So we intend to do one and two together. So that's basically what's written in this page. So to do this, at first we consider the set E plus minus PQ. So now why are we considering this E plus minus thing? Because we are bounding it by D plus Fx and D minus Fx at two ends. So that's why it's plus minus, and where P and Q are rational numbers. So it's defined as X belongs to open parent A comma B, such that D plus of Fx is greater than Q, greater than P, greater than D of D minus of Fx. For each PQ belongs to Q. So now we have an observation. The set E plus minus of PQ is measurable, and to show this is measurable, we need to show that D plus of Fx is greater than Q, and D minus of Fx less than P. These two sets individually are measurable, so their composition is measurable. So now we need to use another lemma from Shiva and Atreya, which I didn't prove here because we are just using this lemma. The lemma is called lemma star. The lemma is defined as, let P be a probability measure defined on the Borel set R comma BR. Then for all E belongs to BR, and for all epsilon greater than 0, there exists an open set U such that E is contained in U, and P of U is less than P of E plus epsilon. So this is what we will use. So now let's consider the measure of the set we have done. It's with respect to Lebesgue measure everything. So that is equals to alpha. So now clearly alpha is less than infinity, because this is what we can show. I mean, it's obvious uh, by some small calculations. The set E plus minus PQ is a finite measure. Now let epsilon be greater than 0 be given. Now by lemma star, we can find open set U belongs to Rn, which we can actually decrease the bound to R, U subset of R, such that E plus minus of PQ is a subset of U, is contained in U, and lambda of U is less than alpha plus epsilon, because it says that the set is contained inside U such that E is contained inside U, and P of U is less than P of E plus epsilon. So here E is E plus minus PQ, this set, and U is our basically the open set we are considering. So as lambda of E plus minus PQ is alpha, we have considered this is less than alpha plus epsilon. So now for each x belongs to E plus minus PQ, there exists a function h of x such that in the open neighborhood around x, of h radius, ixh, which is defined as the open radius, open ball, I have just defined, that is contained inside U. Now we have this notion that from the construction of E plus minus PQ, because we have considered D plus and D minus. So in that case, as if and also as f is a non-decreasing function, so this thing makes sense because we have considered it in this way. This is greater than P. So the H comes here and this thing, this dagger comes. The dagger is valid. And now for all H less than equal to Hx, this holds for all H less than equal to Hx. Now since let us consider a cover or a set of a collection of open neighborhoods of such IHXs we have defined before, such that X is in E plus minus PQ and H is less than H of capital H of X, small h of X. Now we claim that this is the vitally cover for E plus minus PQ. Now why this is a vitally cover for E plus minus PQ? Because let us just go back to the recall the definition of what the definition of vitally covered. So it is a vitally covered if it has a neighborhood H I such that lambda of I is less than epsilon and A is contained in it. So now observe that it is the neighborhood is contained in U, and of course this is less than epsilon because we can consider pH to be epsilon or P to be epsilon. I mean in that manner, and because PQ was arbitrary in Q by our construction. So now by as it is a vitally covered for E plus minus PQ, we may by lemma 1 find a subcollection H x minus H sub I plus X plus H sub I, taking the HI radius neighborhood around X for all I belongs to 1 to N. And note that capital I of small suffix I, which is we are defining these small neighborhoods as uh, is contained inside mathcal I, the vitally cover, such that the intersection of these two union, disjoint union of I equals 1 to N I of I is greater than alpha minus epsilon. Lambda of E plus PQ intersection, the disjoint union of capital I sub I is greater than alpha minus epsilon. So let us call this double dagger. And now this makes sense as a disjoint union, but for future reference, we will be denoting it as just the union. Now, for any y belongs to the union, the set E plus minus PQ intersection I running from 1 to N I of I, there exists K of y such that the neighborhood which we are defining as the uh, as j of y minus y plus j is a subset of I for some I belongs to 1 to N. And also note that f of y plus j minus f of y is greater than qj. Now, why are we considering this intersection? So by considering this intersection, we are actually eliminating all the possibilities of less than cases, the d minus fx case. So now we are considering the d plus case. So by the configuration of e plus minus, yes, d plus of fx is greater than q. From there, we can actually say that uh, this is f of y plus j minus f of y is greater than qj. Let us call this triple dagger. Holds for all j less than equal to k of y. Uh, just like we showed for h of x, for all h less than equals to h of x. Now, since this cover, the collection j such that j belongs to j of y of j such that y belongs to e plus minus pq intersection I running from 1 to n I such that j less than ky, like the last construction we did for the d minus fx less than epsilon p case, less than p case. So now we, by the similar argument we used last time, we can show that this is a vitally covered for e plus minus pq intersection I running from 1 to n I of I. And similarly, by lemma 1, which we proved in the first PDF, there exists and double dagger. We can find a subcollection J1 of the double dagger relation is this subcollection J1 to JL such that a finite subcollection, sorry, J1 to JL such that lambda of E plus minus PQ intersection J running from 1 to L, JL is greater than alpha minus 2 epsilon by the similar argument. Let us call this star. So now as each interval Jj, where J belongs to 1 to L, is contained in some interval II by the construction as we have constructed it, because it lies in the intersection of the union. And if it is contained, if each interval Jj, because it is why it is contained, because let's take an X belongs to Jj. So now observe that Jj is considered as J of Y such that Y belongs to this. So if Y belongs to this, then Y will also belong to the union. So if Y belongs to the union, then at least Y belongs to some capital II, right? So any Jj of Y will be a subset of I of I for some I belongs to 1 to N by the construction I just explained. Thus, now we have an inequality P into X minus alpha, X plus alpha plus epsilon is greater than P into lambda of U by the construction we did at the very first, considering the open set from the lemma star we did. So this is less than equal to P of P lambda union of I, because all the I's were contained in U, so and their union is also contained in it. So basically, this is less than equal to that, and that equals P into summation k equals to 1 to n h of k, where we are defining it to be h of k, which is less than 2 summation, and h of k is, remember, h of k is that thing, we defined the neighborhood to be h of I here. Yeah. So now this is less than 2 summation I running from 1 to n f of xi minus f of xi minus hi by dagger. Dagger is the relation f of f of x minus f of x plus x minus h is less than ph, I think. Yeah. Dagger. So from there, we can actually turn it to a double sum, because it's 2, right? So like if we run it from k equals 1 to n, and then run it from j such that jj, which is contained in I, f of yj plus kj minus f of yj, because we have actually, at first we considered a larger set. Now we have what can I say, compressed it a little. So now for the first case, for the first compressing, for the first neighborhood compressing of the radius h of I, for I belongs to 1 to n. After that, we compress that interval further into some y in around a point y in that neighborhood, uh, to with a radius of kj, where j belongs to 1 to n. And now, why does this hold? Because f is non-decreasing. This thing. So now, basically, it becomes j running from 1 to L, f of yj plus kj minus f of yj, 2 into, that is less than 2 into q, sorry, summation I equals to 1 to n ki. This comes from, I think it is triple dagger. Let me just, yeah, it is triple dagger. So this relation, this line comes from the inequality we used, we saw previously, triple dagger. So thus, by the previous argument we used in this case, similarly we have that will be less than equal to the disjoint union, which will be greater than equal to q into alpha minus 2 epsilon, which we have seen earlier, this alpha minus 2 epsilon by star. Now, as epsilon was arbitrary. It shows that P of alpha is greater than equal to Q of alpha because we can take epsilon to be 0 or epsilon approaching 0 in that case, that sense, because it is a strict inequality, but we can consider epsilon to be 1 by n and then approach into infinity. So P, that's why this less than equal equality sign is also there. So P alpha is greater than equal to Q of alpha. Now, since P is less than Q by our assumption, we can conclude that alpha is 0. So thus we have shown that the set E plus minus PQ we considered earlier, which was for D plus and D minus, where the sets where the differentials don't agree and are bound and they're not equal. So in that case, it has measure 0. So now, thus this is for the two terminal cases. Now we can, by the similar argument, we can actually show that should show this for the sets E minus plus, E plus plus, E minus minus. Those, they also have level measure 0. And what will the sets look like? E minus plus will be D minus fx, and it will be bounded by D sub plus, D power minus to D sub plus, D power plus, D sub plus, D power minus, D power minus, D power minus, D sub minus. This is the thing we have. The construction of the sets will be like this. And by the similar arguments we did now, in this proof, for the E plus minus case, we can show that they also have measure 0. So thus, this proves that it is not differentiable somewhere, but it is differentiable almost everywhere. And the point and the set where the function is not differentiable and f, or f dash doesn't exist has measure 0. So thus, f dash exists where the function f dash exists has measure 0, because lambda because the set we considered has positive measure, finite measure. Now this is for the third case. The third case was we need to prove that integration a to b f dash x dx, that is less than equal to fb minus fa. Yeah. Now let us define one thing. If we consider x to be greater than equal to b, let us define fx to be f of b, to make it constant. So now for h greater than 0, let's define f of h, f of sub h, which is from a comma b to r plus, as f of h x equals to f of x plus h minus fx by h. Now we can observe that easily, that is the domain is r, the range is r plus, because this is f is a non-decreasing function. So fx plus h for h greater than 0 is greater than 0, and this f of x plus h, f of fx h is greater than 0. If we considered h to be less than 0, still in that case it would be greater than 0, because this inequality will be less than 0, and then this will be less than 0. It will basically cancel out and become plus. Yeah, so this is the same thing I said earlier, that these functions are uh, positive, non-negative. So now this is measure. The set is measurable. F dash is measure. The set f dash is measurable, and it is non-zero, and it is non-zero. So thus we can use Fatu's lemma here. So by Fatu's lemma, we have integration a to b f dash x dx. Oh, sorry, I forgot to give the dx. Yeah, that is equals to integration a to b limit h tends to 0 fh x dx, because we have defined fh to be this. So limit h h going to 0, that will be basically this. So now by Fatu's lemma, in this step we are using Fatu's lemma. So the limit comes out, limit h tends to 0, a to b fx plus h minus fx by h dx. That is by the definition of fh x. So now the 1 by h comes outside, and it's integration b to b plus h fx plus fx dx minus integration a to a plus h fx dx by substitution. So now observe that fx, the function fx, is now defined inside the interval b to b plus h, where h is going down to 0. So the thing is, when we define this, already we have defined that if x is greater than equal to b, then fx is equals to fb. Thus, it will become just a constant. Oh yeah, I have explained it. So thus it will become fx equals to fb. Thus 1 by h integration b to b plus h fx dx will just become 1 by h into fb into h. B plus h minus b. That will just be fb. And then it will just be like this. In the next step, the limit will go inside. And now as f is non-decreasing, we can just have this as it is less than equal to fb minus fa. So now this establishes that f dash is integrable with respect to Lebesgue measure, hence finite, and and why it is finite because this is less than this finite bounded. This completes part. So thus this completes the whole my presentation. Thanks to Shreyam for some tidbits and some help, and so to some MSc second year brothers for their help. Thank you. Can I stop sharing? Or just... Sir, you are muted, sir.
Yeah, you can stop sharing. Yeah. I mean, I think it was too much to observe, so people may not have. And some people have left also, I believe. So I hope they will watch the video.
I think just there are 4 people.
Yeah, only. So they will watch the video, I believe, over later when they have time. Okay, so the next person can start. Actually, today we have permission from CMI permission, so it will not restrict for 45 minutes. We can continue with the next talk. Next person.
So can I leave?
You want to leave? Okay, you can leave. Okay, who is going to talk next?
Yes,
Shreyam,
I will
no?
just watch the video.
Yeah.
Okay, so I'll just continue from where you left. So in the beginning, we'll start with some basic definitions. The first one is okay.
You go ahead.
So in the beginning, we'll just define what a partition is. It's basically like you take any interval and you divide it into particular points where x0 is basically the starting point and xn is the last point, and in between you have the other points. And we'll denote all the partitions of the interval AB by P of A comma B. Now we'll define what's a bounded variation. So suppose you have a function f from the interval AB to R. It's said to be of bounded variation if you consider the sums of the form, the mod of fxi minus fxi minus 1, where xi lie in some partition. You take the sum over all xi and you consider the supreme over all partitions of the interval AB. So if this quantity is finite, then we say that f is of bounded variation. And if it's of bounded variation, we can also refer to T as the total variation of T. Okay. So now we'll look at, like, there are only 2 theorems. So this is the first, and this is the first one. A function f is of bounded variation on the interval AB if and only if it's the difference of 2 non-decreasing real functions on AB. So this is a if and only if statement. So let's prove both the directions. First, assume that we can write f as g minus h, where g and h are both non-decreasing real functions on the interval AB. Then for any subdivision or any partition, we can...
You haven't changed your page. Only the first page is showing.
Yes, sir. I'm continuing the first page only. Like,
Oh, you are tracking in the first page only. Okay. Okay.
So if you take this sum, we can write this as this is less than equal to the sum over all gxi minus gxi minus 1 plus the sum of hxi minus hxi minus 1 by triangle inequality. And further, we can write that this is less than equal to this finite quantity by using triangle inequality, as this is a telescoping summation. So from here, you can say that the total variation of f is finite. Now let's prove the other direction. So for that, we'll define x plus to be the maximum of x and 0. And we define x minus as the negative of the minimum of x and 0. So from here, it's easy to observe that both these quantities are positive because the minimum of x and 0 is negative, and when you take the minus of that, you get a positive quantity. And using these definitions, you can observe that the mod of x is basically x plus x minus, and x is equal to x plus minus x minus. So now we'll define 2 functions. The first one is PA of x, this is basically the supreme over all partitions of AB, and you take sums of the form fx xi minus fx minus 1, and you consider the plus of this. And in the same way, you'll define NA of x, which will be the supremum of minus of the difference minus. So, like we observed here that both these things are positive. So using the same argument, you can say that PA of x and NA of x are both non-negative, and they're bounded and non-decreasing functions on AB. So now if you define your partition to be x1 to xk, then you can write fx minus fa to be equal to this. This is basically the telescopic summation. But again, we know that x is basically x plus minus x minus. So using that identity, you can write this sum.
You haven't typed these things, or you haven't? No, I mean, how will people visualize whatever you say? I mean, you are making many mathematical statements. Unless people see it, how is it possible to do that?
No, I mean, like, I'm using this, like, I wrote the identity, it's just substituting that. That's why I didn't write all this. It was,
Shreyam,
yeah.
I think, I mean, you're just like, right now I can just see the table of contents. Is that intentional or?
Is it?
That's what I was
Oh.
asking. Is there? No. I think you are saying
No,
something
it's
which is
written.
not written.
Oh, it's not showing. All
Yeah,
right.
yeah.
Oh,
We
That's
can
what
only see the index.
Change your.
like now is it moving? Oh, okay.
Ah,
sorry.
yes. That's
Oh,
what.
okay, all right.
Yeah.
Then I'll just start from this theorem. Like
Yeah.
the definitions are easy. Like I just defined what a partition is. This is normal, what we did in Riemann integration. And then I'll define what a bounded variation is. It's basically, we consider sums of the form, the mod of fxi minus fxi minus 1 over any partition, and you take the supreme over all partitions of AB. So if this quantity is finite, then we say that f is of bounded variation. So these were the two definitions. Now the first theorem which we were looking at was this, that if f is a bounded variation of AB, it's a bounded variation on AB if and only if it's the difference of two non-negative real functions on AB. So since this is a if and only statement, let's look at the first direction. Assume that it can be written as a difference of two non-decreasing real functions on AB. So from there, we'll prove that it's a bounded variation. So if you consider any partition of the interval AB, then you can write this. This is basically summation of I equals 1 to n, this difference. Using this identity, we can write that this is less than equal to this by using basically the triangle inequality. And this is further less than equal to this using the same triangle inequality. And as this quantity is finite, we get that the bounded variation, which is this quantity, is also finite. So f is of bounded variation. Now let's prove the other direction. For that, we'll define x plus to be equal to the maximum of x and 0, and x minus to be the negative of the minimum of x and 0. So from there, it's easy to observe that this quantity and this quantity both are positive, as this is the minimum of x and 0, and you take the negative of that. So both these quantities are positive. And in the same way, you can observe these two identities, that modulus of x is basically x plus plus x minus, and that x is equal to x plus minus x minus. So we'll be using these identities in the proof. Let's define two functions. The first one is basically PA of x, which is you take the summation of this form. You consider the plus part of, basically the positive part of fxi minus fxi minus 1, and you take the sum over all k, and you consider the supreme over all partitions of the interval AB. And in the same way, you define NA of x, which is just the minus, and you take the supreme over all partitions of AB. So using this identity, which we have over here, we observe that both these quantities are positive. So in the same way, we can say that both these functions are positive. I mean, they're non-negative, bounded, and they're non-decreasing functions on the interval AB. Now you consider some partition of the interval AB. This identity, like fx minus fa, is basically the summation over I equals 1 to k of xi minus fxi minus 1. This is just the telescopic summation. Now we know that x is x plus minus xi minus. So using that identity, you can further break this down as the summation over the plus part and the minus the summation over the minus part. So from there, you get that this summation, sending this minus part to the other side, you get that the summation over all plus parts of fxi minus fxi minus 1 is equal to the summation over the minus part plus fx minus fa. And you consider this equation and you take the supreme over all partitions of the interval AB. So this function basically becomes PA of x. This function becomes NA of x, and you have fx minus fa. So sending this to the other side, you get that fx is equal to PA of x minus NA of x plus fa. So in the beginning, we proved that both these functions are non-negative and non-decreasing in the interval AB. So this proves the required claim. So we prove both the directions, that if it's a bounded variation, it's a bounded variation if and only if it's a difference of two non-negative, non-decreasing functions on AB. So now we move towards the fundamental theorem of calculus, and we have a proposition about differentiability. So suppose that f lies in L1 AB comma lambda, where lambda is some arbitrary measure, and you define the function fx to be equal to the integral from a to x of f zeta d zeta. So this is differentiable almost everywhere, and f prime x is equal to fx almost everywhere. So without loss of generality, we may assume that f is positive, and as f lies in L1 of AB comma lambda, we have that fx is equal to this thing, and this is a non-decreasing function, and f prime of x exists almost everywhere. So we'll break this down into two cases. The first case is when f lies in L infinity of AB comma lambda. In that case, f is basically bounded. So we pick some arbitrary c lying in the interval closed A open B, and by the dominator converges theorem, this integral a to c of f prime of x dx, this can be written as this thing. You keep this constant and you break this down like using this definition. So now from here, you just switch the limit and the integral sign to get 1 by h outside. So you have this, and now resubstitute the definition of fx into this to get that this part is basically the difference of the integral c to c plus h minus a to a plus h of fx dx. Okay, so we are interested in the limit h approaching 0. So you can assume that h is small enough such that a plus h and c plus h both lie in this closed interval. From the definition, it is easy to see that f is continuous. So if I pick some u lying inside c and a and fix some epsilon greater than 0 for sufficiently small values of h, if I consider this thing, the modulus of this integral minus fu, observe that fu is basically like fu times, it's 1 by h times integral from u to u plus h of fu. So writing this as 1 by h, and then using the fact that the modulus of the integration is less than the integration of the mod, you can bring 1 by h outside and the integration outside. So inside you get this function fx minus fu. And since it's continuous, this is less than equal to epsilon. So this entire quantity becomes less than equal to epsilon. And observe that by the definition of fx, fa is basically equal to 0. So from these equations and the fact that fa is equal to 0, we get that the integral from a to c of f prime of x is basically fc minus fa. And as this thing is 0, this is basically equal to f of c, which is basically integral from a to c of fx dx, right, from the definition. And as this is true for any c lying in the closed interval a comma b, you can say that f prime x is equal to fx for almost everywhere for x lying in a comma b. This is basically a theorem of Shiva and Atreya, which states that if the integral of some function is equal to 0, then the function is equal to 0 almost everywhere. So from this, and if you consider this and this, if you take fx that side, you get that the integral from a to c f prime of x minus fx is equal to 0. From there, we can say that f prime x is equal to fx almost everywhere. So this was the case when f lies in L infinity. Now consider that f lies in L1 a comma b, ab comma lambda. We define a new function f capital K of x is equal to the minimum of fx and k, where k is some positive real. So using the definition of fk, you can observe that f minus fk of x is greater than equal to 0. So we define a new function gk of x, which is the integral from a to x of the difference of these two functions. So this is a non-decreasing function, and hence it's differentiable with a non-negative derivative almost everywhere. So we differentiate this quantity, and again observe that this function can be written as this. We are just we just use the fact that derivatives can it's like the derivative of f of f plus g is equal to derivative of f plus derivative of g. So these two cancel out. So you have this, but this thing is positive because we got here that this function is differentiable with a non-negative derivative almost everywhere. So this is a positive quantity. So this function is greater than equal to the derivative of this, but this on the other hand is just equal to fk of this should have been fk of x. This is just this is equal to fk of x. So this just gives you a case one where fk is bounded, and if you allow k to tend towards infinity, you get that f prime of x is greater than equal to fx almost everywhere. This is one equation that we get. Thus, we can say that integral of a to b f prime of x dx is less than equal to fb minus fa. This is the last theorem which Richik proved in his presentation. So using this, this thing is basically equal to the integral from a to b fx dx from the very definition of capital F of x. So from here you get that this difference is greater than equal to 0, and from here you get that difference, the integral of the difference is less than equal to 0. Using these two equations, you can say that the integral is equal to 0. And again, using this theorem that integration of f d mu is equal to 0 implies f is 0 almost everywhere. So from here you can say that f prime of x is equal to fx almost everywhere. This was the theorem that we wanted to prove. So that's it.
Yeah, you can continue.
Can you give me a moment, sir? I'm just trying to share screen.
Sure.
Yeah. So can you, can you see my presentation?
Yeah.
Okay. So, so a large part of what Richik and Shreyam, what basically this whole topic of differentiation was leading towards is the fundamental theorem of calculus. Okay, so first we basically so we start with defining with a definition of absolute continuity. So so this is just a definition, and it's quite apparent from the definition itself that this is something that is stronger. This is a variant of continuity that is stronger than even uniform continuity, because here you can see that here we're allowed to take all finite collections of pairwise disjoint. So we can in particular just take a collection comprising a single interval, and then this goes through for all such intervals wherever we place them within our domain. So that's essentially just the definition of uniform continuity, that we can make this smaller than epsilon by using the same delta for so that will work for all of those intervals wherever we place them. So this is so this is stronger than even uniform continuity. So this is a definition we needed to begin with, and now we have a proposition. So this basically is some implications we're drawing out from a function being absolutely continuous. So so if a function is absolutely continuous, then it is of bounded variation, and as for the part and hence differentiable almost everywhere, this part will use theorems that Richik and Shreyam have proved. So all I will show is that it is of bounded variation, and then we show that, well, now that it is differentiable almost everywhere, we can make sense of its derivative almost everywhere, and then if it so happens that it is 0 almost everywhere, then it's a constant. So so we can see right off the bat that how stringent this condition is, because it's giving us differentiability almost everywhere, which is obviously far from the case with, say, regular continuity. You can construct an easy example of a function which is continuous everywhere but differentiable nowhere, and this is so much stronger than that we get differentiability almost everywhere. Whereas here, usually it is the case that we say that, okay, if the derivative is 0 everywhere, then it's a constant. But here we have weakened that hypothesis due to absolute continuity. We can weaken that hypothesis and say it need only be 0 almost everywhere, and then it must be still a constant. Okay, so we just have one hypothesis, which is that the function is absolutely continuous, and so we just write down, this is just from the definition of absolute continuity. So we've just written that out. Okay, so but so what at least in proving the first part of this proposition, probably the most important step is this one, this inference which we draw from absolute continuity, that if I is a closed and bounded subinterval of length of AB of length less than delta, then it's the total variation of f restricted to I is less than or equal to epsilon. So to see how this happens is that, so here if you look at this definition, so what we have is that, okay, this clearly basically tells us that if I, so you can think of it as having like I have, so I fix epsilon, I'm given an epsilon, I fix it, and now now I have there exists some delta greater than 0, such that, okay, I will work with that, you can think of it as a length to work with on the real line, on the input. So if I think of the graph of this function, because it's a, you can think of the graph quite easily because it's a function from a closed and bounded interval to R. So we can talk about this graph in the plane as usual. We can think of it this as having, you know, some length, a length delta to work with on the input axis, which is the x-axis. And the idea is that, okay, I can sort of intuitively, you can think of it as I can split up this length delta into as many parts as I like, and those parts, of course, only finitely many parts, but that finite number could be anything. And those parts themselves could be located anywhere within AB. So you could take 2 parts or 10 parts, and the individual parts may be located anywhere in AB. These intervals are the parts I'm referring to. So and still, when I look at the, you know, the image of those points, and then I look at their, if I look at the sum, it will always be the case that it's less than epsilon. So what that means is that if we take a closed and bounded, now here the reason we emphasize closed and bounded is because we wish to talk about the variation and in turn the total variation of f restricted to I. So that's why we've taken that it's closed and bounded. If it is of length less than delta, then surely if I partition it, then all the parts, okay, so let me partition it. A partition will determine, you know, will naturally determine a collection of intervals, closed and bounded intervals, but I can just, you know, omit the endpoints, and that gives me a finite collection of pairwise disjoint intervals. So it's clear that then that the sum of their lengths, this is just the sum of the lengths of those intervals, that will be less than delta, simply because the length of I is itself less than delta. And then it follows that the variation, so this, so here we are just talking about an arbitrary finite collection. When this finite collection so happens to be the one induced by a partition, then this will in fact just be what we call the variation of our function on that interval. This is just the variation. So that basically tells us that, well, the variation with respect to any given partition, because we can take any given partition here, the variation with respect to that partition will certainly be strictly less than epsilon. And so taking the supremum over all those partitions, we get that the total variation is less than or equal to epsilon. Okay, so now next we, so now the idea is that, okay, this is what we've done. We managed to show this. And now if we choose n large enough, so certainly, I mean, this AB being a closed and bounded interval, it has finite length, and we can certainly choose n large enough so that we can divide this into n subintervals, each of length less than delta. And we're using this simply because then we can use this. Call these I1 to In, just the finite collection of intervals we have. And so this essentially is referring to a partition. So we have a partition in which each of the thus determined intervals has length less than delta, and these are those intervals. And for future reference, I will call this partition tau n, tau sub n. So okay, so we have these intervals, and then simply it's just, I mean, the obvious implication of this is that so t sub ij is less than or equal to epsilon for each of those, because here it was any closed and bounded subinterval of AB of length less than delta. So therefore, just summing over, J, we get this. This is what we get. And now notice here that this is simply this is not so n times epsilon is not some arbitrarily small quantity, because you notice that n is clearly a function of delta, and delta in turn is a function of epsilon. So n is a function of epsilon, and as I make epsilon say smaller, n will naturally grow larger. So this is simply all this is telling us is that this quantity is certainly finite. The sum of these total variations is going to be finite. Now I claim that the total variation of my function sort of globally is precisely equal to this. And if I can justify this claim, I will in fact be done, because that would imply that the total variation of my function is finite. And that is precisely what bounded variation is. Okay. So yeah. So it is obvious that this sum is simply, so we can call this, and it's justified to call this the variation of our function with respect to a certain partition, with respect to the partition pi. So this is the variation, and that actually justifies what we mean by bounded variation. We've shown before that basically a function is going to be of bounded variation if the total variation is finite. And it's quite clear by the definition of the total variation that it's an upper bound on, so if we choose to call these variations with respect to a partition, then the total variation is an upper bound for those. So if it's finite, then certainly this becomes bounded. So hereafter we will at least verbally be referring to this particular sum as we'll refer to it as the variation of our function with respect to the partition pi. So it is obvious that this sum, this variation with respect to pi, where pi is any partition of AB, it increases under refinement. This is because, this can easily be shown. In fact, I mean, you can think of adding one more point to our partition, and then you can proceed via induction. And the idea is, when we include one more point, when we refine our the given partition pi with say just one more point, then if that point so happens to lie in a section where say the graph, our function is sort of monotonic within that subinterval, then there will be no change actually within the sum. But obviously a priori we don't know that it's going to be monotonic within any given subinterval. So, and if it isn't monotonic, then we can certainly it will certainly increase. That is quite easy to see. So it increases under refinement, and in particular, just proceeding via induction, we can say that well, if I consider the variation with respect to a partition pi, then the variation with respect to the refinement via tau sub n. So I just include all the points in tau sub n, which we have determined previously. So this sum is the variation with respect to this must be greater than or equal to this. So yeah, so what I mean to say is basically that, okay. So moving on. So thus, in the definition of the total variation of a function, the supremum can instead be taken over refinements of tau sub n. This is just immediate from this, because the supremum is an upper bound, and so for each partition we have a sort of a better candidate to use for a supremum. So for each one determines, in fact, I believe, yeah, a unique superior candidate in taking so we can take the supremum over refinements of tau n. This is the archetypal refinement of tau n. This is what it looks like. Okay, so clearly there is a one-to-one correspondence between refinements of tau n and partitions of the intervals determined by tau n. So these are simply those. In that, a refinement of tau n induces and is in turn induced by partitions P1 to Pn of I1 to In respectively. That is just obvious. I mean, if you take any refinement of tau n, then that naturally gives us, so I don't think we need to bother with justifying this. And moreover, for such partitions, we have, this is just obvious. I mean, this is just by almost, I mean, this is immediate. There's no justification needed here at all. So now that we have this, so this is basically saying that the variation of a function, the sort of the global variation over our entire domain A, B, that is going to be the sum of the individual variations. So assuming, of course, you fix some partition P of, so refinement P of tau n, and that uniquely determines these partitions, which is why this makes sense, and vice versa. So so the variation with respect to this particular refinement is simply equal to the sum of these variations, the individual variations. Okay. So, and now just taking the supremum among such partitions, which we have as we can take the supremum merely over refinements of tau n. So we take the supremum among such partitions, and it follows that the total variation. So this is simply justifying a claim which we had made previously. This is the claim, and we were actually done because this shows that this is bounded, or rather this is finite, must be finite, the total variation. So this shows that the total variation is finite, and it proves that f is of bounded variation on AB. It is consequently differentiable almost everywhere as the difference of two non-decreasing real valued functions on AB. Now this part, this particular consequence is a result of, this is a theorem which was proved by, it was proved that by Shreyam that that any function of bounded variation, so a function is of bounded variation if and only if it is the difference of two non-decreasing functions on AB. So it is this part was proved by Shreyam, and each of those, so each of those are differentiable almost everywhere. This was proved by Richik. So so this proves the entirety of part 1 of our proposition. Now, as for part 2, we will show that f of c is equal to f of a for any c within our interval. So consider just this set. So recall that, of course, we know that our function is differentiable almost everywhere. So we look at those points. So first of all, we consider any c within this closed interval a, b, and now let's look at those points within this open interval where the derivative is 0. So call that set E, and obviously note that the Lebesgue measure of E is c minus a, because we had assumed that this is zero. Our function is, the derivative of a function is 0 almost everywhere. That's our hypothesis actually. So let eta greater than 0 be given. Then for every x, so for every point within this set E, there exists h, so that will depend on x. It's a function of x greater than 0, such that so all this is actually just an obvious consequence. This is literally just from the fact that the derivative is 0 at any given point at the points within E. The derivative is 0 there, and this just follows from that. And of course, it's an easy task to just take the minimum of what we found via the derivative being 0, and also we want this particular interval to stay within this. And this is an open set, so we can always find an open interval. So we just take the minimum of those two, and we can take that to be h of x. So certainly this is going to be within open interval a, c for all h less than or equal to h of x, as well as this. This is simply by the derivative being 0. Now observe that this is a Vitali cover of E, this particular collection. So we just go, so we just take all the points within our set, vary across all points in our set, and all h less than or equal to h of x. Okay, I think, this ought to be basically h of x. So this gives a Vitali cover fee. Vitali covers were talked about by, I believe, Richik. And again, as proved by Richik, this is something that Richik proved, that we can find a finite disjoint collection of intervals, disjoint collection of intervals within our Vitali cover, such that this is true. This is just from something he proved. This is precisely what he proved. And here delta, of course, is the delta which we have fixed before. This is our delta. So yeah, we had fixed epsilon, and thus there is, by hypothesis, there is a fixed delta. So we've fixed that, and each time we refer to delta after this, it is that same delta. So such that this is less than delta. Now let us call, so within this finite collection of intervals, let us just denote each of them like so. Then by 2, so then by this, what we get is, this is what follows. And this is simply because, we're just summing over those intervals actually. So for each interval, we knew that this quantity is less than n times of, h. So it was formulated slightly differently, but this is what we had. And then we just sum over all that finite collection of intervals. And this in turn, so obviously this sum is clearly less than C minus A. Okay, so this is what we have. And whereas by 1 and 3, this is what we get. Okay, so 1 is, this is our very first hypothesis. And by 3 is this. So using these, it is immediate that this is, so basically this is everything that is, this basically represents the part that is, or rather this whole entire thing represents the part that is, this thing. And if this has measure less than delta, then we know, if it had measure less than delta, and these are being intervals, their measure is just going to be the sum of their, individual, they're all disjoint. So the Lebesgue measure is just going to be the sum of the individual lengths. And then by 1, it follows that this entire thing is less than epsilon. Thus, this is what we have. This is just, you can just, we're actually just expanding this out and also using the triangle inequality. So this just follows from this. And this in turn is, again, now we're just using 4. So this is going to be less than epsilon plus, so epsilon plus eta times C minus A. So of course, since epsilon and eta were arbitrary, it follows that, so they can be made arbitrarily small. So basically these are arbitrarily close and equal, so as required. So this completes the proof of the second part of our proposition as well. Now we have in order to prove the major theorem, which is the fundamental theorem of Lebesgue integral calculus, we first require this lemma, which is actually which actually completes one way of the implication. So this is what we have. Okay, so we just consider a disjoint union of intervals. So we have a disjoint collection of open intervals in open A comma B, and let's define E to be this set. We have, so this is just, this is just immediate from the definitions. And here, of course, this is again just from the triangle inequality. And then this is precisely just what we mean by the integral over this set E, it being disjoint. So this makes sense. Okay, this is some portion which we will need to finish this proof. That this is less than or equal to this. Okay. So now we have a claim. We say that for each epsilon greater than 0, there exists delta greater than 0, for which this is the case. So first of all, so let's fix some epsilon greater than 0. So given any epsilon, so we consider some epsilon greater than 0. By the definition of the integral of a non-negative integrable function, there exists a simple function. So this is, of course, just a function of the epsilon which we chose. So a simple function. This is the class as denoted in the book by Sundar and Atreya. This is the class of non-negative simple functions. So there exists a non-negative simple function such that it is, less than or equal. So this is the function which we wish to approximate. So that it is less than or equal to mod f on AB, and also that, yeah. So this is simply by the definition of the integral of a non-negative integrable function, which in this case is mod of f. So that this is, yeah. So you can make those arbitrarily close, basically. So this is what we have. Certainly f. So f being greater, f minus SC. I believe there ought to be perhaps a modulus here. Yeah, I think it should be modulus of f minus s epsilon is greater than or equal to 0 on, yeah. So if if a set within a subset of this is measurable, then by linearity and additivity over domains, this is just very easy. So by linearity, we can just take these under the same integral. But of course, I mean, if we are integrating over a smaller set, so E is a measurable subset of A comma B. So if we replace the integral from A to B with simply the integral over E, then that must be less than or equal to this. And then again, we use linearity to get this. So this is just immediate actually from this. On the other hand, this S sub epsilon being a simple function, so it has finite range, and thus it's certainly bounded. So let this be some upper bound for it essentially. So therefore, again, as before, this is measurable, then this is what we have. So this is what we have here. So we just add this integral to both sides, and then is less than or equal to 0. If we replace this with m throughout, then that must be greater than it, and times, of course, the measure of E plus epsilon by 2. So this is actually all of this. So setting delta is equal to epsilon over 2m, we observe that 7 holds for this choice of delta. So 7 is this. Yeah, and that's certainly true, because yeah, if we take, so if that basically tells us that the measure of E is less than this quantity, so this whole thing is less than epsilon by 2. So this whole thing is then less than or equal to epsilon, or rather, I think strictly less than epsilon. Yeah, so that's what we have. So this 7 holds for that, and that really proves our claim at least. And now note that, so again, if we are given any epsilon greater than 0, it follows from 6 that, so actually the same delta that we have determined here, it works as in the preceding claim. It responds to this epsilon challenge with respect to the criterion for the absolute continuity of, so this follows from 6, because, okay, if we have managed to, so we showed that when the measure of E was less than that particular delta, we showed that this entire integral was less than epsilon, which means this thing is less than epsilon. But that is precisely what absolute continuity is, because yeah, we managed to make the sum of those, the sum of those, yeah. So yeah, so we found delta basically such that yeah, if the sum of those lengths is less than delta, then so this proves the absolute continuity of F. This proves our lemma actually. Now finally we've come to the fundamental theorem of Lebesgue integral calculus. This is actually relatively far easier, especially since given all the prerequisites we've proven already. So 2 implies 1. This is in fact precisely more or less the content up to just this addition of this constant. It is the content of the preceding lemma. So this is just immediate. As for, so now we wish to prove that, okay, if it's absolutely continuous, then this is the case. So, okay. So by the proposition we've proved, we know that F is differentiable almost everywhere. This we have. And in fact, we know that it was in fact first we showed that it was a bounded variation, and that is equivalent to saying it's the difference of two non-decreasing functions. So let these be the non-decreasing functions f1 and f2, and let f be equal to the difference. So hence this is what we have. This is just by the definition, and yeah, all of these are actually obvious. All of these are completely, this entire thing is completely obvious. So this basically, I mean, this being bounded by this sort of real number, this finite real number, this shows that f dash is integrable. And lastly, we have that this function is, it follows that this function is differentiable almost everywhere. Why is that? Because if f dash is within this, we have already shown that yeah, if given a function within so given this integrable function, then this function, the indefinite integral of it is differentiable almost everywhere. This is what we've shown. So further, the derivative of d at x, yeah, so you can easily see that this is equal to 0 almost. So being differentiable almost everywhere, we take the derivative, and this just works out to be this. So it's 0 almost everywhere. And from as we've proven before, this implies that d is a constant function. This was proven in the second part of the proposition. So it's the derivative being 0 almost everywhere implies it's a constant function, and therefore d of x is equal to d of a for any given x, of course. And this is just, if you just literally just substitute a into this, then this follows right from that as required. So this proves, this completes the proof of the fundamental theorem. Okay, so.
Yeah. We have only 2 audience. So if you have any question, you can ask. Otherwise, we will end the session. Okay, thank you. We will end the session and we'll meet at 5.
Thank you, sir.
For the next session.